Okay, all right. So new section for today. We're in section 1.5 now. We're talking about lines and planes. By the way, in case you haven't noticed, what we're doing right now doesn't really have any calculus in it, right? In order to be able to do multivariable calculus, we kind of first have to work on the multivariable part, and so that's why we're doing things like defining vectors, and now here we're going to talk about certain kinds of objects in R2 and R3, more so R3, of course. And we're going to continue in that direction, talk about, more about how to describe things in R3 and other kinds of, shapes and surfaces, and we're going to try to get some good familiarity with R3 first, and then we'll start doing calculus pretty soon after that. Okay, so how do you talk about lines and planes in R3? I'm going to start off with a refresher. Lines in R2, and I know that goes way back to middle school, big yawn, right? But I'm going to show you a point of view on this that you probably haven't seen before. So, reminder, now I know y'all know this equation right here, y equals mx plus k, right? Old news, equation of a line, right? And you know this equation, ax plus by equals c, also the equation for a line in the xy plane. So between these two, which one is more geometrically natural? I'll ask. If you'd asked me when I was in middle school, I would have said, "Oh, clear cut, no question. Y equals mx plus k," because that m means something. The m is the slope. Slope is geometric. The k means something. That's the y-intercept. That's geometrically natural. It's something you can see on the graph. This is loaded with geometric intuition. And this ax plus by equals c, what I was told in middle school is that this is just, it's kind of organized. Let's get all the variables over on the left. Anything that's not a variable, we'll put it on the right. And it's at least organized. And I remember thinking, okay, that's a pretty sorry reason to have an equation of a line in a certain form. This was not a fair presentation that was given to me. And okay, it was middle school. They couldn't really show me at the time what I'm about to show y'all because this, it was middle school, not a multivariable calculus class. So, this is the one that now I think is the most geometrically natural, really. And let me show you why. Takes a little bit of doing, but I want to start off with a presumption that we know certain information about this line. I want to figure out how to derive the equation. What's a reasonable way to derive the equation of this line? And what I'm going to tell you about this line are two things. I'm going to tell you a point on the line. So point, right? If you want to think of it as a vector, you can think of it as that position vector. And then I'm also going to tell you another vector. Let me just cut. That vector being a perpendicular vector. Right now, I claim that, geometrically this does characterize the line. If you tell me a point, and if you tell me that the line's got to go through that point, and it's got to be perpendicular to that end vector, there is only one such line. All right. So, given this characterizing information, how would we find the equation of that line? Now, what do I mean by an equation? An equation is a test. If I come to you with a point X, and I want to know, is that point on the line? Or perhaps, maybe this is X. Is that point on the line? How do I decide if some other point X is or is not on the line? An equation is that thing. Y'all know this, right? The way you use an equation to test is you take the point that you want to test and you stick it into the equation. If the equation works, then yes, it's on the line. If the equation does not work, then no, it's not on the line. Okay, so how would I test points? And I claim what it comes down to is looking at this difference vector. Right? If the point is on the line, then the difference, x minus x naught, will be parallel to the line. And furthermore, if the point is not on the line, then x minus x naught will not be parallel to the line. Yeah? Okay. All right. So that's the approach we're going to take, and let's just talk about the point that actually is on the line there. So let's come down here and do a little bit of algebra. The point is on the line if that difference vector is parallel to the line. Now, another geometric appeal, being parallel to the line means it's perpendicular to that n vector, because don't forget n was perpendicular to the line. Okay, so parallel to the line means perpendicular to the n vector. Okay, now I hope y'all just had a knee-jerk mental reaction when you see something like this, specifically when you see one vector perpendicular to another vector. Your knee-jerk reaction should be, oh, dot product is 0. Right? This is a very powerful property of dot products. More to the point, this is a powerful connection between algebra and geometry. One of the big tools in math is to take, geometric observations and figure out how to write them algebraically, because algebra is how we do business. That's how we get stuff done, right? And geometry is usually kind of what we're wondering about, what we're trying to understand. So being able to take questions that we want to understand and phrase them in a language in which we can get stuff done, that's how you solve problems. So making the connection here that perpendicular to n can be written as dot product with n is 0. That's kind of it depends on how you look at it, but this is one of the big important ideas in what we're talking about here. Okay, and now let's actually do some of this algebra that we were just talking about. So happy about the fact that we can do a dot product distributes. I refer you to the algebraic properties of dot product we talked about last time. Well, I guess it was Monday. But so you distribute, and then you take this term and whip it over to the other side of the equation here, and what you end up with is n dot x equals n dot x naught. And now let's think about this n vector. This n vector is going to have some coordinates. Let's see, where did I write this down? N has some coordinates. Let's just call them a and b, whatever. They're just numbers. X naught also has some coordinates. X naught, it's just some point. So it's got, let's say, x naught comma y naught, whatever. And notice the right side of this equation now, you can just crank this out. That's a number. N was given, x naught was given. Dot products, we know how to compute. Crank it out. That's some number. And the left side of the equation, dot product with this n vector, that left side becomes ax plus by. And lo and behold, here it is. There's that equation that I was not so impressed with when I was in middle school. And we see that this equation comes out of a natural geometric argument that you can make. But arguably more importantly, this equation has natural geometric information encoded into it. This equation, these numbers, A and B, mean something, right? Going back up to here, we were super impressed with this formula because the M and the K mean something. We didn't know what the A and the B meant. Now we know what the A and the B mean. The A and the B tell you a vector perpendicular to the line. So the A and the B tell you something that we couldn't have talked about in middle school, right? So I forgive my middle school math teachers. We didn't understand vectors in middle school. We certainly didn't understand dot products in middle school. So this was inaccessible at the time. But now it's important to recognize that this is a really great way to think about lines, because this gives you a geometric foot in the door. This gives you a vector, a meaningful and important vector associated with that line. And it's really nice in that sense. Okay. All right, so was the purpose of this conversation to clean up a middle school lesson? No, not at all. This is going to generalize. So I'm going to show you what this looks like in 3 dimensions. We're going to make morally the same argument. Let's suppose I want to talk about the equation of a plane, and there's different ways that you could write the equation of a plane. But I'm going to show you the one that I think is, again, the most natural. So suppose that I know a vector perpendicular to the plane and a point in the plane. And again, I appeal to your geometric intuition. If you know that the if you know that the plane we're looking for goes through that point and is perpendicular to that normal vector, well, perpendicular to that in, if you know the normal vector points a certain way, that pretty much tells you how the plane is oriented. And it really only allows you sort of one degree of freedom of how you move the plane. And then there's only one such plane that actually goes through a given fixed point. So these two pieces of information characterize the plane. Just like they did with the line, by the way. Note the analogy. With that given, I want to test under what circumstances is a point in the plane versus not in the plane. And look, everything else in this argument is morally equivalent. In the plane would mean x minus x naught is parallel to the plane and therefore perpendicular to the in vector. A point not in the plane would mean x minus x naught is not parallel to the plane and therefore not perpendicular to n. So you can decide, when is a point in the plane by writing down the same algebra. Here it is. Difference parallel to the plane, perpendicular to n, dot product equals 0 is what perpendicular means. Distribute, thank you, algebraic properties of dot product. Good thing we wrote those down. Boring though they were, but you got to use them. And there you go. There's n dot x equals n dot x naught again. Looks like the same equation. Don't forget, though, that this n is now a perpendicular vector in 3 dimensions, so it has 3 coordinates, A, B, C, to dot with the 3 coordinates of the x vector that we're testing, x, y, z. And therefore, even though at a glance, symbolically, this looks like the equation for the line in 2 dimensions, it's actually the equation of a plane in 3 dimensions. How are we doing? Everybody on board? Okay. All righty. Okay. A little bit of lingo. I called this vector n to conjure this word normal. In this context, the word normal means perpendicular. In other contexts, the word normal means other things. Normal is one of the most overused words in math. Right? At some point, I counted different uses of the word normal that I was personally aware of, and I thought of 6. Completely unrelated, different uses of the word normal. So anyway, apologies for the lack of creativity in the language, but that's the terminology in common use. That's why I used in and why I call it a normal vector. Okay. So, quick example, suppose you want to understand the equation of a certain plane, and you know that it goes through that point and perpendicular to that vector. You want to find the equation of that plane. Well, going through that point, x naught, wrong color. Through that point, there's our x naught, perpendicular to this vector there. That is therefore our in vector. And this equation becomes this. That's just a little bit of plugging and chugging. Pretty good? Okay. All right. Here is a different example. Here I'm not going to give you a normal vector. Here I'm going to tell you we're again looking for the equation of a certain plane. What I'm going to give you is 3 points in the plane. Now, you look back up here at our equation. Our equation requires only that I have 1 point, but it very clearly requires that I know an in vector, right? I've got to have that in vector. I was not given an in vector. Are we dead in the water? Well, no, I'm just going to have to do a little bit of additional effort to figure out what that normal vector is. The idea is that if you were given 3 points in the plane, then a little bit of geometric creativity allows you to find a normal vector. So here's how that geometric creativity goes. We have pairwise, I can take differences like so. If the points that are given are in the plane, then these differences are parallel to the plane. Now I have 2 vectors parallel to the plane. With 2 vectors parallel to the plane, how would I find a vector perpendicular to the plane? Well, I need to find a vector that's perpendicular to both of the 2 input vectors. Where have I heard that phrase before? Cross product. Right? So we're going to compute what we can satisfactorily call a normal vector in by taking B minus A cross C minus A. So what we've got here, let me point to where we do that. Yeah, there you go. B minus A cross C minus A. So what we've got here is an example of a creative application of concepts that we've learned about our various algebraic tools. Right? So it's one thing to know how to compute a dot product, how to compute a cross product. What we're doing here is capitalizing on how we understand the meaning of a cross product, properties that it has, and then further creatively recognizing, without having been told, that is the tool that we need. Right? So anyway, there's a lot of thinking that went into this particular example in that sense. Did I see a? Yeah, okay, yeah.
What's in the point C? The vector C, sorry.
I'm sorry?
The vector C.
Yeah, what about it?
So I think we were given the point was...
Oh, yeah, so we were given A, B, and C in the statement of the question here. So there's A, there's B, and there's C.
There's 1, 0, 1.
Yeah. My picture is not to scale. Yeah, it's, you're quite right. Where I've drawn that C is clearly way off. But, very often what we'll do is, if, certain things that don't actually matter, we won't think about in the representation in the picture, right? So in other words, all I was trying to communicate here is that in, gives you differences that are parallel and cross products make it perfect. That's all that really matters here. And, where I put the picture. Yeah,
so how do you know whether the vector B minus C is supposed to be given?
Yeah, so that's an option we could have done if we had wanted to. Instead of doing these two, I instead could have done these two, and it would have given me a parallel normal vector. Yeah, in fact, depending on which order, it might have given us the same vector. Yeah, totally. Great questions. Anybody else? All right. Okie dokie. So, by the way, y'all are going to notice on the homework that there are several questions that are, I'm going to say, in this general direction. And what I mean by that is that there is a puzzle component to the question. Namely, it's not going to be, here's the givens, plug them into the formula, chug, right? But it's going to be, here's some information that's not technically exactly what you're looking for. You figure out how to, cleverly combine, subtract, cross, whatever, right? To turn what you're given into what you need. And your guide in solving those puzzles is thinking about, from what we talked about last time, all the different connections between algebra and geometry. What do cross products look like? What do dot products do? This kind of thing. Yeah. Okay. Yeah. Mm-hmm.
I don't remember why is it minus A?
Oh, yeah, it was kind of arbitrary. I was just making the observation that if these 3 points are in the plane, right, then when you pairwise subtract, see, A is in the plane and B is in the plane, and therefore their difference has got to be parallel to the plane. Does that make sense?
Would it not matter if we did like A minus B and A minus
Yeah, totally. No, it doesn't matter at all. So, you could totally instead do, A minus B and A minus C. Yeah. I mean, I did these for, I don't know, I guess I was just feeling uncreative. Right? But, yeah, either, again, you can do that and this. Totally cool. As long as you take differences here's what you can't do. You can't do that and that. Because now those are parallel and the cross product can give you 0 and it's just not helpful. Yeah.
So you could do B minus A and A minus, like you don't have to.
Yep. So B minus A and, A minus C. Totally fine. Yeah. As long as they're not parallel, as long as they're not parallel to each other, but they are both parallel to the plane, then the cross product has to be good.
So just in general, X and X naught are arbitrary.
In the equation of the plane, in this equation here.
No, like when you're setting it up.
In this kind of a question here.
Yeah.
Yeah, it's pretty arbitrary. I mean, you're always responsible to make sure that what you're doing makes sense. Right? So what I don't want to do is give you carte blanche to here, you have my permission to not think about whether what you're doing is okay. Right? So you got to make sure that, again, don't, do B minus A and A minus B. And more to the point, of course, your goal here shouldn't be I want to be prepared to handle 3-point questions. Right? I mean, this is just suggestive of a category of questions. And so you always have to kind of think through, what do I really need to be true, and is it in the choices that you make as pertains to a particular question? Yeah. Anybody else? There were a bunch of hands at some point. Did I get to everybody? Okay. Alrighty. Okay, so let's see. We've talked about lines in 2 dimensions. We've talked about planes in 3 dimensions, and they were very analogous. In both cases, notice the object that we were interested in, here a plane, right? The planes are 2-dimensional, was 1 dimension less than the world that we were thinking about it as sitting inside of. Right? So a 2-dimensional plane inside of a 3-dimensional space. A 1-dimensional line inside of a 2-dimensional XY plane. So what I want to consider now is what do you do if that pattern does not hold? What if you have a line in 3-dimensional space? And I claim that this whole idea of, look, it's entirely characterized by a normal vector, it's not true anymore. It's just not, right? I mean, so for example, let's think about lines in space that are perpendicular to, let's say, that normal vector. Well, there's a lot of lines perpendicular to that normal vector. There's one. Here's a different one. Right? There's arguably there's a whole plane, you might say, of lines that are all perpendicular to that same normal vector. So this whole approach that we were taking crashes and burns badly. Right? We're going to have to take a totally different point of view on how to understand lines in R3. So here's the idea. I'm going to say, look, a line is characterized by, you got to give me a point in the line, and then I'm going to ask that you give me a vector parallel to the line. And that's a different geometric strategy. Okay? But it remains that the direction vector v, I'm going to call this a direction vector. This direction vector is pretty much telling me how the line is kind of oriented, if you will. And then once I tie it down to it having to go through this point, then we're done. That's all that line. The line has no more flexibility. There it is, only one such line. Okay. So parallel, not perpendicular. This is just geometrically different. Geometry has algebraic consequences, therefore we're going to get something that's algebraically different. And here's how it plays out. given that x and that v, how would I decide if a point is or isn't in that line? Well, again, I'm going to look at the difference vector. That difference vector either is parallel to the line or is not parallel to the line. Therefore, either is or is not parallel to the direction vector. Right? And to have a vector, x minus x naught, parallel to a vector, this is where, when we were looking at the, in the previous cases, we were like, ooh, dot products. Well, we're not looking at perpendicular anymore. Now it's parallel. So one thing you could do is you could say, hey, how about cross products? But it turns out and that's fine. That would give you a point of view. But there's an even easier way to do this, and that is that if these are parallel, then that's a multiple of the other, and that's just easier to write down. So this is what you get. So x minus x naught is a multiple of v. By the way, I don't know what this multiple is. That t, I don't know. It's some multiple because they're parallel. And notice that tells you that this mystery point x that we're trying to decide if it is or is not on our line has to be of this form. It has to be x naught plus tv for some value of t. Now this is not algebraically like the results we got in the previous cases. And so, well, yeah, it's geometrically different, algebraically different. It's even kind of strategically different. Let me point out that this is let's see, the way this statement connects to points is different in the following sense. This is not a test, right? Equations that we've come up with in the past, n dot x equals n dot x naught. It's a test. You come to me with an x, plug into that equation, and it's either yay or nay. Either it works or doesn't work. That's not what this is doing, right? If you come to me with an x vector or an x point and say, hey, is this point, I've got this point x, is that point on this line? How do you decide if the equation works or not? I don't know what t is. Do I have to figure out, do I have to solve then for whether there or is there not some t that makes this work? So immediately then, this is not working the same as an equation. And that's disappointing. But I want to point out that this has a different advantage. This is not a point tester. This is a point generator. If you come to me with a point and want to test it, I'm sorry, I can't really help you. But if you say, hey, start throwing points at me, start cranking out points that are on this line, no problem. I can plug in any value of t into this expression. Whatever value of t I plug in, let's do t equals 3. Plug in, boom, there's a point on your line. Yeah? T equals 5, point on the line. T equals 7, point on the line. T equals 16, point on the line. And I can just crank out points on the line. Equations don't really do that. Right? So it's different. Pros and cons. Right? It's kind of a different kind of a thing. So we call this a parameterization of the line. It's going to turn out to be a big deal. Having equations for geometric objects is nice, and there's some cool things you can do with them, and there's a bunch of things you can't do with them. Having parameterizations is a neat way to describe a geometric thing, and you can do stuff with parameterizations that you can't do with equations. And some of the things that you can do with equations, you can't do with parameterization. So anyway, it's another tool in our toolbox. This is one of my favorite metaphors. You should think of mathematical objects, mathematical knowledge, each little snippet of idea that we talk about is another tool in your toolbox. And for certain kind of problems, hammers are awesome. But if you need to screw a screw into the wall, hammers are not very useful. You need a screwdriver, right? But then if you have a screwdriver and you need to hammer something into the wall, screwdrivers aren't very useful. So it's nice to have a toolbox full of a bunch of tools, and then you use the appropriate tool in the appropriate circumstances. So new tool, and we'll see how to use it over time. By the way, a lot of that will be in chapter. Some of that will be in chapter 2, and but a lot of it will be in chapter 6. I think it is. I've forgotten the chapter numbers. I think the last chapter. Parameterizations are going to be a really big deal. Okay, so suppose I want to parameterize a line. So I want to do this. And what I'm given is that the line passes through these 2 points. Now again, notice we have not been given exactly what we need. In order to make a parameterization, I need one point in the line, and I need a vector parallel to the line. I am not here given a vector parallel to the line. So I've got to play the puzzle again. Where's my picture? I had a picture. Yeah, here we go. I'm given this, and I'm given that. How am I going to find a vector parallel to the line? Well, no surprise. Subtract. There's a vector parallel to the line. I'm going to use that as my direction vector. Everybody good? So there's always going to be these kinds of little, puzzle. There's a puzzle aspect to a lot of these kinds of questions. And so now once you have a vector parallel to the line and a point in the line, by the way, take your pick. You could use A if for some reason it seems more natural, but it does not matter. If you want to pick B, that's totally fine. Suit yourself. But there you go with a point and a vector, and you're all set to go. Okay. How are we doing? Okay, let me show you how I can combine these ideas. This is I think, kind of a cool example, and that is we're going to look at the line from this previous example. So let me just circle. There you go. There's our line. And I would like to know, where does that line intersect this plane? How would I find a point that's on both that line and that plane? Okay, so now the way, different ways you can answer these questions, but a great way to answer this question, I think, is to remind ourselves, what are these objects and what fundamentally do they do? I have here a point generator to generate points on our line. I do not have a point generator for points on our plane. But I have a point tester. I can test points that are on the plane. I can't test to see if some point is on our line. Okay? So we can generate points that are on our line, and then we can test to see if they're on our plane. That's the tools that we have to work with at this point. So how about let's just do that. Let's look at all the points that I can generate and test by plugging those points into here. Let's test whether they are in fact also on the plane. So we're going to rewrite this this parameterization here as xyz equals 4 plus 3t, 3 plus 0t, I'll just call it 3, and then 1 plus 3t. There's our x, y, and z. Give me any value of t and plug it in, and there's a point on our line. If I want to then test whether those are on the plane, I take these generated points and I plug them in to test whether they are also on our plane. Everybody see what the strategy is there? Yeah, we're about to. Yeah, absolutely. So every value of t that I plug in here is going to give us an x and a y and a z. This being a point generator, I know for sure that x, y, and z are on my line, and I just want to know, is that x, y, and z also on our plane? And I decide that by plugging it into our point tester. So here's how we plug that in. I'm literally going to write down x plus y plus 2 times this z, and see what happens. And so here it is. There's our x, and there's our y, and there's 2 times z, and that gives us this equation. And now I've got to decide, did it work? Are these points on the plane? Well, sometimes. This equation, you can go through and solve for t and see t has to be -1. What that means is that if t is -1, then this equation is satisfied, and therefore the point that was on the line is also on the plane. That's the point we're looking for. Right, so you take this deduced value of t and plug that. You have to plug it back into the parameterization to see what is that resulting point. And there it is. It's 1, 3, -2. Everybody good? Yeah.
Is the only way for like a plane or a line not to intersect is if they're parallel?
In 3 space, yeah, that's right. And yeah, so what we've shown here is that that's not the case, which is good. Yeah, great, absolutely, yep.
So how do we know it wasn't?
Well, it has to be on the plane because we got to this by saying we require that the point we've generated be on the plane. Does that make sense? Yeah. And from that requirement, we deduce. Okay, well that means t is -1. Is that cool? Okay. So maybe let's sink in. Yeah, sure. Anybody else? Is everybody okay? Okay. All right. Okay. So we've got these parameterizations. What if, given the parameterization, what if, though, you say, I really do need to test the points, though. I've got a point generator. I understand it's a point generator. Yes, tools in a toolbox. I need a tester. How do I find the equation or whatever for a line in R3? And there's a great way to do this. It's a very clever argument. Here's the idea. Here's our parameterization. You can see we generate a point x, y, z by it being our starting point on the line plus t times our direction vector, ABC. Now, by the way, let's solve for t in all of these equations. I get t equals x minus x naught over a. It's also y minus y naught over b, and it's also z minus z naught over c. Okay. So, all right. Well, so what does that tell me? Well, I've got 3 different formulas for t. Now, we didn't really dwell on the following note, but let me just remind you that when I say, this is a point generator and you can plug in any value of t you want, you've got to pick one, right? There's just one value of t that you plug in. You can't say, for the x coordinate, I'm going to plug in this value of t, and for the y coordinate, I'm going to choose a different value of t. No, you pick one value of t, and that'll compute the point. Single value of t gives you all 3 coordinates. Said differently, if a point is in fact generated by that single value of t, that single value of t has to equal to all of these things. Does that make sense? So, if t has to equal to all of these things, then all of these things have to equal to each other. And look at this, we have, it's like it's an equation, but it sort of looks more like 2 equations. And now let me actually propose this is kind of 3 equations. Because I need for these 2 things to equal, I need for those 2 things to equal, and then I also need for these things to equal. Yeah. Okay. All right, and this is a point tester. So if you come to me with a point, x comma y comma z, whatever that might be, you say, look, take your generator and go somewhere. I don't need the generator. I don't need other points. This is the point I care about. I need to know, is this point on your line? Well, you plug into this thing, And if all three of these things are equal, then all three of these things are the value of t that generates your point x, y, z. Yeah? Okay. And therefore it is on the line. So there you go. So this is, by the way, what we call the symmetric equations of symmetric equations for the line. And it's a nice little argument. By the way, if on an exam, just for this is, I don't know, I feel the need to point this out, but on an exam, if I give you a parameterization and ask you to find the symmetric equation of the line, there's been a long history of students just sort of ignoring the argument and just saying, "Oh, I see the pattern. Whatever is that, this goes there and that goes there and that goes there," and just sort of say, "Oh, template," and writing this down. And just a reminder, that's not an argument. That's not a thought, right? This is a class about ideas and a class about communicating, reasoning. I went on at length about that on the first day. So I always want to see some indication that you understand that the way you get from here to here is that t has to equal to all of these things, and therefore these things have to equal to each other. So give me the argument, right? Don't just transcribe. Okay. So quick example. Here's a parameterization. What are the symmetric equations? Well, t has got to equal to that, and it's got to equal to that, and it's got to equal to that. All of these things have to equal to t, and therefore all of these things have to equal to each other. Okay. All right. Yeah.
Does it mean that if any of the coordinates of the vector is 0, t doesn't exist? Oh,
no. Well, then you get some different algebra. Yeah. If one of the, if c was 0 or something, here, let's play with that. So let's suppose, the equations that you're going to end up with just don't look very symmetric. But let's suppose that this is 0, right? In which case all of that's kind of gone, right? Then, well, I do need for x minus x naught over a to equal to y minus y naught over b, because both of those things are equal to t. But then notice I do have a third equation, and the third equation is just straight from there. It's just z equals z naught. And so there's our point tester, right? The point test in that case would be these two things have to equal to each other, and z has to equal to that value. Yeah, it's a great question. Yeah. Yep.
So if you have two different sets of points that both equal like a different value of t, would those be like on two different lines?
I'm sorry, I guess I'm not understanding. So two different, what now?
Like if you had one set of points and that equaled like one value.
When we say one set of points,
like one coordinate.
Like so 1 point with 3 coordinates. Okay, yeah. I'm sorry, go ahead.
And they like equal a certain value t, or they'll equal that t value.
Yeah.
And then you had a different one and that equals a different t value. Are those two different lines?
No, they're on the same. So if we're talking about the same symmetric equations, and it is the same line, right? Uh-huh. So if you plug in one x, y, z, and you get that this is 13, and that's 13, and that's 13, then it's on the line, and it's on the line at the point where t equals 13. Different point, different coordinates, that makes this equal to -3, that -3, and that -3, still on the same line. It's just, it's on that line. That's the point that's generated when you plug in this different value t equals -3. Yeah, good question. Yeah, absolutely. Anybody else? Okay. Alrighty. So here's a fun little exercise that I enjoy going through. And that is, okay, symmetric equations and all that, but let's look at just that equation by itself. What does that mean? Is that anything? Is it geometrically connected to the line that we're interested in? And if so, how? And it turns out that yes, it is. This is a really naturally connected geometric object to the line. And it's actually it's a really easy little line of reasoning to see what this object is. I'm going to make a couple of casual observations about that one equation. First of all, move some terms around. That's the equation of a plane. Right? And you cross multiply and move some terms over to one side. That's going to be something times x plus something times y plus something, 0, times z equals something. That's a plane. Okay, so we have a plane. Here's the other thing. Any point that's on the line, which therefore satisfies both of these equations, any point on the line, due to satisfying both of these equations, also satisfies that one equation. Well, of course it does. Trivial, right? If it satisfies both, included in those both is that one. What that means is that every point that's on our line is on our plane. That means that this plane, we've agreed that this thing in green is a plane, this plane contains our line. Everybody good? Okay. Third thing I can observe about this plane, we already made the observation that here, let me write this down. I suppose I should jot this. This is, something x plus something y. Y'all can work out the algebra if you care to. Plus 0z equals something. And the fact that this is a 0 means something. Right? Remember, these coefficients in the equation of a plane are telling you about the normal vector. This normal vector has its third coordinate as 0. So this normal vector is horizontal. I don't know exactly which direction it points horizontally, but it doesn't have any upward component. So we have a normal vector that is horizontal, and if you have a normal vector that's horizontal, your plane is vertical. So what we have here in green, this is the unique vertical plane that contains the line with these symmetric equations. And I've got a picture of that drawn here. It is like this. It's what I like to call the vertical shadow of our line. Here's our line. And just imagine, sun straight up, sun rays coming down. The shadow cast by the line that we're interested in would be a vertical plane containing the line. So that's that plane. Okay. Yeah, are we good? So I'm going to leave as the following then as an exercise for you guys. This is a healthy exercise, I think. So this, we just agreed that equation is this plane. I want you all to persuade yourselves that if you look at the equation involving just the y and the z, right? So that part of the symmetric equations, that gives you the shadow, if that would be cast by L if you were to shine a flashlight from over here in the x direction, which you might call the YZ shadow, and then analogously that colors. This one with the x's and the z's gives you the XZ shadow. So it's a nice exercise. The argument is totally analogous to what we just talked through, but with different variables playing different roles. And so the symmetric equations then, a different way to think about the symmetric equations for a line is that the symmetric equations for the line are a way of viewing, of understanding the line by way of its various shadows, parallel to different axes. Okay, so I think it's a cool little exercise. It's a nice little bit of mathematical weightlifting to make sure that you're understanding the ideas that we've been talking about. Okay, moving along to the next section. I'm going to be super quick in this section. It's a section on coordinate systems. It's basically we're just going to talk about polar coordinates, cylindrical coordinates, and spherical coordinates. Some of y'all have seen some of these coordinate systems in the past. Polar coordinates, I think a lot of you may have seen. No big deal. So the idea of a coordinate system is it's a way of describing a location by way of certain numbers that we call coordinates. So y'all remember the rectangular coordinate system. If you want to describe a point in 3 space, right, then x, y, and z coordinates, describe this location. Well, we call that a rectangular coordinate system. You can probably guess why. When you draw the picture, you get this rectangular box. Okay. So the thing is, there are other ways to describe locations with coordinates that don't involve drawing boxes. And for example, right, I could take this point here, and while, yes, I can describe its location with its x and y coordinates, that's a rectangular description of where that point is. Totally different way that I could describe that location is by talking about what is that angle, what we call theta, and what is this, let me loosely say distance, namely, given that you're going in this direction defined by theta, how far from the origin do you go in that direction? I mean, look, if you tell me theta equals pi over 3 and r equals 2, I know what point you're talking about. That describes a location. That's a coordinate system. Isn't that cool? It's a different way to do it, but it works. Okay. So each of these coordinate systems that we're going to talk about, there's different little details that have to be observed. In this system with polar coordinates. I'm sorry, I got a little ahead of myself. Quick point I wanted to make first. This point could be described as x comma y, but it also, I suppose, could be described as r comma theta. And there is sort of I'm going to say question mark here, because now we have this awkwardness of, when you say point equals something comma something, is the first thing the x coordinate, or is the first thing the r coordinate? And you might think, okay, we'd look at the letters. If it says x, y, well, clearly that means rectangular. If it says r theta, clearly that means polar. But what if it says instead, what if it says 1 comma pi? There's a temptation to say, that pi, that looks like an angle. I feel like this could be, probably this is polar coordinates. R is 1, theta is pi. But we got to recognize there is a point where x is 1 and y is pi, and I might want to talk about that point someday. And so what I've written down here is pretty ambiguous. Right? So, context will usually make that clear, but just be aware that it won't always, and you've got to make sure that when you're communicating ideas in writing, you've got to make sure that what you write is clear, right? So, a way that you can get around this is to use subscripts. I like to use a little subscript here when necessary, this little subscript of r to suggest that these are rectangular coordinates, and a subscript here of p to indicate that these are polar coordinates. And so you can remove the ambiguity, what are you talking about here, by you put a little subscript p, and that's just your little note to the reader, hey, by the way, these are the polar coordinates of the point I'm actually interested in. So you can do that. Or, by the way, another thing you can do, perfectly reasonable thing you can do, would be to just say r comma theta equals 1 comma pi. And now there's no ambiguity. Everybody good? Okay, alrighty. So how do you convert from one to the other? Suppose you know the polar coordinates of a point are r comma theta. how would you figure out the rectangular coordinates, x comma y? And it's not hard to persuade yourself from this picture that x is r cosine theta and y is r sine theta. It's a little trig. Hope everybody's good at trig. By the way, reminder, while we're here, there is a prerequisite trail for this course. Math 212 requires that you're good in Calc 2. Calc 2 requires that you're good in Calc 1. Calc 1 requires that you're good in trig and algebra and all that old high school stuff, geometry. So tracing it back, I am going to assume implicitly in this course that you are comfortable and proficient and fully greased and ready to go with trigonometry and algebra and geometry and, of course, Calc 1 and Calc 2. So just a reminder. Okay. All right. Now, I do want to address one other thing here. Let me not get ahead of myself here. But so these two equations, x are cosine theta, y is r sine theta. Once you have these equations written down, a question comes up, which is, does r really need to be positive? It doesn't technically need to be positive. You could think of, for a given value of theta, you could say, look, let r be negative, in which case, we for a given value of theta, maybe here's where r is equal to 0, and here's where r is equal to 1, and here's where r is equal to 2, and sure, but then you could also say, then over down here is where r is negative 1, and etc. Down here is where r is equal to negative 2. And if you were to describe points, locations with this value of theta and using negative values of r, everything works just fine. It's not a problem. And these equations here, in particular, work just fine. And it's kind of nice to leave ourselves that flexibility that we can, if we should want to, choose to view r as being negative. So, for example, that gives us some options. You'll notice then that, here, let me just draw a new picture. What am I doing? That this point here, let's say with x coordinate of negative 1 and y coordinate of negative 1, that point I could describe in a couple of different ways. I could choose to view that with respect to this value of theta, and I could choose to view this as theta equals pi over 4 and r equals negative square root of 2, no problem. Right? Or I could also choose to view that instead from this point of view as theta equals 5 pi over 4, r equals positive square root of 2. So you got options in terms of how you describe points with polar coordinates. This is not familiar from rectangular coordinates. Rectangular coordinates, you have one option, right? A point only has exactly one rectangular coordinate, pair of rectangular coordinates. Not so with polar. And by the way, also with polar, you could equally well choose to view this theta as 9 pi over 4. Now that seems a little perverse, but if you were to go all the way around like that, that gives you that direction, right? That's something here, watch me. I can, see? I'm still pointing that way, right? It would have been much easier to just do that, but an extra spin gets you pointing in the same direction. It does describe that same point. So, in fact, you can also say here plus any multiple of 2 pi. any number of additional spins around still gets you pointing in the same direction. So there's a bunch of little sort of curiosities about polar coordinates, and you want to think through all those possibilities. Okay, so this having been said, I do want to correct something in the book here. I've written that r is equal to square root of x squared plus y squared, and that's really not quite technically true, given that we're going to allow ourselves this flexibility of thinking of r as being negative. Because don't forget, that symbol means positive. So what I should have done is I should have just left this as r squared equals x squared plus y squared. So let me X that out and say, check on this. And as needed, if you do want to solve for the R, then you can, look at your picture, think about your context, make the appropriate decision, either positive or negative, and decide whether this is plus or minus. Right? But in general, this is what's always true and not necessarily that. Everybody on board? All right. Okay. Along those same lines, and I guess I better leave that crossed out. Along those same lines, don't make the mistake of trying to solve for theta here. There's a temptation, ? Can you say theta equals arctan of y over x? It's so tempting to want to do that, but because there's this temptation to get to a conclusion. There it is, we're done, we've solved for it, right? But this, again, takes away your flexibility. Arctan is a well-defined function. It has a single value for any given input, right? So this would force you to only looking at certain values of theta. And they might not be the values of theta that you're interested in. So don't do this either. Tan theta equals y over x is fine. Not as long as x isn't 0, of course. Okay, all right. Of course, if x is equal to 0, your theta is going to be pretty clear because you're on the y-axis, and that's easy, yeah.
Rectangular coordinates can describe R2 and R3, but
right.
There can only be one.
Yes, absolutely. Polar coordinates, as I'm describing it here, is specific to 2 dimensions. That's right. And I will say a little bit more about 3-dimensional version of this in a couple seconds. Yeah. Okay, so that's polar coordinates. Cylindrical coordinates is sometimes referred to as polar coordinates in R3. Yeah, so per your question. And that terminology, I guess, is kind of okay. It's sort of fine. Here, let me walk you through what cylindrical coordinates is. The idea is if you want to describe a point in space, we can do so by first dropping a perpendicular down into the xy plane. In the xy plane, in the xy plane, this projection down here has polar coordinates. Okay? And then you can describe this original point by the polar coordinates of the projection, comma, the z, that describes how far you dropped it down. Okay? So you can see why they call this polar coordinates in R3. It's a rip-off of polar coordinates, right? Nevertheless, I prefer to give this a different name. I prefer to call this cylindrical coordinates. This is the more common choice, I think. Call this cylindrical coordinates. Because if you were to set this variable r equal to a constant and ask, what are the points in space that have a single constant value of r, you get a cylinder, right? Cylinder centered on the z-axis. So cylindrical coordinates is pretty common choice. And there's a sort of a temptation with students to want to use the same name to refer to different things. I don't know, it's somewhat comforting maybe, but I would encourage you to resist that temptation. This really is a different coordinate system, and so why not give it a different name? And I think cylindrical coordinates is the right choice. Okay, all right. Here's one that really is different, though. This next one I want to talk about is called spherical coordinates. Here's the picture. This is a tougher thing to talk about a little bit. Oh, by the way, as soon as we're done with spherical coordinates, we'll call it a first half. We'll take our 10-minute break. Okay, so if you want to describe a point here, we are still going to drop a perpendicular. We are still going to then interpret this angle theta, but we're not going to look at R. We're instead going to look at these other two coordinates. We're going to look at what is this distance, rho. That's the Greek letter rho, by the way. And then we're going to look at this angle coming off of the z-axis. That's the lowercase Greek letter phi. So these three coordinates, a little bit of a weird way to think about it, I suppose, but it turns out this is really natural in some very good ways I'll talk about in a moment. So in some sense, we define the direction out of the origin. The direction toward the point is defined by theta and phi. Right? And given a theta and phi defining a direction, then rho tells you how far to go in that direction. Okay. Quick observation, notice how nice it is to write the equation of a sphere in spherical coordinates. Rho equals c. Right? So that's pretty cool. So one of the nice advantages of spherical coordinates. Everybody on board? We'll talk in a minute about how to convert back between, spherical and rectangular. So one other quick thing I'll say though, another advantage that spherical coordinates has, very often you're taking derivatives of things, you're describing, functions that take place in three variables, and by the way, I can't remember if I've mentioned this before, but my undergraduate background was math and physics, and so in my physics major, I did a lot of stuff with, you have to look at an atom, and the atom has a nucleus, and there's electrons that kind of surround the atom in a certain way, and being able to understand, how to describe the electron in terms of, what variables you choose. Rectangular coordinates don't really make a lot of sense, as it turns out. Spherical coordinates make a lot of sense because we're most interested in, if an electron is sort of over here, how far away it is from the nucleus. That's really natural. That's important. That's intrinsic to the way the atom works, right? So this spherical coordinate rho really important. So when you do quantum mechanics in the hydrogen atom, spherical coordinates for sure easiest way to work. Okay, and that's just one example. Okay, so how do we convert? There's an easy little trick to making that observation, and that is to start by looking at this little triangle right here, which I observe is a right triangle, right edge with the right angle there. And then notice that this thing here, this thing here that we previously called R, I can write down very conveniently in relation to this angle phi. R is rho sine phi. Everybody see that? Just look at the yellow triangle. We've got a right angle here. The angle phi is there. Memories of trig. R is rho sine phi. That's a really handy thing to remember because it allows us to instantly write down x and y coordinates. X, don't forget, we already know x is r cosine theta. Here, let me write this a little bit differently. X is r cosine theta, and y is r sine theta. Right? Well, yeah, but R is rho sine phi. So rho sine phi cosine theta, rho sine phi sine theta. And that's 2/3 of the work, you might say, in converting from spherical to rectangular coordinates is just looking at this one little trig triangle and noticing that, oh, our old familiar friend R is rho sine phi, and then plugging that into existing previously established formulas for x and y. Great little trick. Is everybody happy with that? By the way, let me circle this a little bit better. R is right there. Okay, the last formula is, for z, well, that's just sort of the other side of the triangle, if you will. Z is rho cosine phi. So that one little triangle, in some sense, answers all our questions. Everybody happy? Okay. Last observation, if you want to convert an equation from let's say rectangular coordinates to spherical coordinates, or, well, let's see, what are we doing here? Oh, here we're doing polar, that's fine. So we want to go take an equation from polar coordinates from rectangular coordinates into polar coordinates. Here is a rectangular equation. You'll recognize this as a circle centered at the point A, 0, radius A. Right? How would I write the equation for that circle in polar coordinates? All you have to do is it's no big deal at all. You just plug in x equals r cosine theta, and you just plug in y equals r sine theta, and off you go, and just, simplify. No big deal. And note that the result is, this is another equation. This, however, is an equation that's in polar coordinates. It's giving, instead of y and x related by algebra, this is now r and theta related by algebra. Yeah.
So if you were trying to go from an equation that had a theta in it to there's like a polar.
So you want to go from polar back to rectangular?
Because you can't.
Yeah. No, you're quite right, and that is trickier. And so that's a much longer discussion. I would say the best way, get lucky, right? Have it be an equation where you can recognize right there in the equation, oh, hey, check it out. There's an r cosine theta in the equation. I'm just going to replace that with x. So yeah, but in general, it's hard. And I will say usually not reasonably tractable. Yeah. Okay, last comment, and then we'll break for 10 minutes. Last comment is, I can shorten this process by being clever. Now, I wanted to show you the sort of the generic process, plug in for x, plug in for y. But if you're clever, notice that here, there's an x squared plus y squared, and I already know that x squared plus y squared is r squared. So why don't I save myself a bunch of trig simplification by just plugging that in the first place? So, heads up, look for opportunities like this. I mean, you won't always get lucky. You won't always just, kind of fall in your lap like that, but every so often it does. And so, take advantage when the opportunity comes up. Okay, so that's a great stopping point for, by the way, I believe we just finished chapter 1. So we'll start with chapter 2 after the break. See y'all in about 10 minutes. Sorry to go a little over for the first half.